Hello. Thank you again for having us. My name is Matt Leese, and I'm going to be talking today about information retrieval for statistical language modeling. I'm going to start the talk by defining exactly what I mean by information retrieval and describe a classic approach for it, the TF-IDF framework. After that, I'm going to introduce the more recent language modeling approach for IR. And the take-home messages, I think, for the talk are really to try and get your head wrapped around the conceptual model if you haven't seen this before, because it's a little different. And what are sort of the basic framework, the basic pieces you need to apply this approach. And then the connection to TF-IDF, because there is a really interesting and strong connection that helps us give a little more intuition for what's going on. I'll talk about a couple simple extensions to it that also, I think, give more intuition for what's understanding on, and they're also very, very core, I think, to how it's being applied today. In terms of evaluation, I'll discuss the important metrics being used, the data that's most commonly used in terms of evaluating English IR systems, and some results highlighting some of the methods I've discussed. I'll talk a bit about my research. I'm sorry to also disappoint you, but this is new work for me, and so I won't be presenting my own results today. I'll be surveying the field a little bit, but I think it should still be interesting. And I'll talk a bit about the ideas, the directions I want to go, and it would be great if people have some feedback on that. And then I'll talk about a few other interesting research questions or other directions I think you could take this work. Also, I think we have plenty of time, so if anything isn't clear while I'm talking or you just don't understand anything I say, please feel free to interrupt me as I go along. So, to get started, what is information retrieval? Well, broadly speaking, it's just finding any sort of relevant information corresponding to a user's expressed information need. This could be textual information or even non-textual information such as images, sound, multimedia, this sort of thing. And there's all kinds of tasks that are useful, whether it's filtering information, categorizing it, summarizing it. And this is an information age we're in now. We have no shortage of information, but we do have a shortage of tools and methodology for dealing with all of it. So there's plenty of work to be done here. In terms of the task I'm going to be talking about today, just specifically ad hoc text retrieval. This is one of the most classic and oldest problems in information retrieval. And the task is defined as this. You're given a collection of text documents, which I'm just going to refer to as docs often, a text query from the user, and the goal is to retrieve relevant documents from the collection. So if you use Google, as most of us do, this is basically this task. The difference, of course, is I don't have any sort of hyperlink structure, or usage statistics. So there's just text in terms of how you find these relevant documents. Yes, classic problem with a long history. You see the citation I have above. Karen Spark Jones, 1972, was doing some very interesting work on this vector approach, which I'm going to start by presenting. So the classic approach is just to represent the query and the document as vectors over the vocabulary in the collection. So for each of them, the value of an entry in a vector is just the number of times the word occurs in the query or document. And the way you would determine relevance between the query and the document is you take these vectors, you just put them end to end and look at the angle between them. And if there's a smaller angle, they're more similar, and therefore the document is more relevant to the query. Now, you can do important refinement of this is to not just, let me just say. So refinement is to use TF-IDF. TF, term frequency, tells us basically the relative importance of a word in the query or document. So the more frequently a word occurs in the document, the more salient, the more important that word is to the context of the document as a whole. And so if the word occurs in the query, this document is more likely corresponding to it. Now, you don't want to bias longer documents, because longer documents may well have the word occur more often compared to shorter documents. So it's important that you want to normalize, basically, documents for length. So you want to talk about the percentage of the word in the document relative to the other words, not the absolute counts. The other important aspect is inverse document frequency, and this tells you how specific is this word in the collection of documents as a whole. So if a word in the query is the, that will probably occur in every document in the collection. And so it doesn't matter if it occurs often because it's not very discriminating. But if the word is, for example, mitochondria, that probably only occurs in a couple of the documents. So this is one that you'll want to give a little bit of boost to. And IDF is just expressed most simply as the number of documents in the collection divided by the number of docs the words occurs in. So, so words that occur less frequently will get a little bit of a boost in that product. Advantages of this approach is it's simple, fast, and it's been very effective in practice. This has been the workhorse for ad hoc text retrieval for many years. The downsides of this approach is in order to get these things work most optimally, you have a lot of little tweaks with little theoretical justification, lack of a full understanding about why these things are working or how we want to change them to improve performance further from here. An example of this, one I want to mention particularly, is these TF and IDF numbers you calculate in this way aren't used in this direct way. You often want to dampen them, for instance, by taking the log of them. And some intuition for why this is done actually comes out of the language modeling approach, which I'm going to talk about next. So Spark-Jones in '72 is talking about inverse document frequency. In contrast, 1998 is when this language modeling approach first gets proposed, so about 9 years ago. So just to get started, what is a language model? It's to define a probability distribution over possible word sequences. So in language, there's any number of possible things we can say, and a language model will give you a probability distribution over each of those possible word sequences. So example model, unigram, or bag of words, is a very simple language model. It just says that the product of the entire sequence of words is just going to be expressed as a product over each of the individual word probabilities. So you're going to throw out in that model any notion of the order the words occur in and just simply look at their individual frequencies. And application-wise, language models have been heavily used in speech recognition and machine translation. So there's a lot of theory and methods available for using them today, and I'll come back to this in a little bit. In terms of information retrieval, what we want to do is we want to estimate a language model underlying each of the documents in the collection. So for each of the documents, we're going to assume that it's some sample from an underlying distribution. And we're going to rank document relevance proportional to how likely the query is under each of the document language models. Okay, so for each document, we have a language model, this probability distribution. We say how likely is the sequence of query words under this distribution. And if the query is more likely under one document's language model than the other, we say that document is more relevant. So this is the basic approach. Now, some intuition for maybe understanding what's going on here. If you think about it, a query and a document often talk about the same information in different ways. You have a sort of paraphrase mismatch. So you can imagine that if the document were infinitely long, you would probably find some paraphrase of the information that does match what's being used in the query, and you wouldn't have this mismatch. So what's going on here in some sense is we're using this language model as an intermediary between the query and the document. And so even if the words in the query don't show up in the document, they do show up in this language model if we can estimate it correctly with some non-zero probability. And hopefully that'll be enough for let us determine what is the relevant documents. And so the challenge, of course, is given that we only have this short document, this finite sample from the underlying distribution, how do we estimate this true language model? So you want to start out by taking maximum likelihood estimation. This basically says in a unigram model, what's the term frequency for each of the words in the document? So if the is 5 out of the 10 words in the document, the will have a probability of 50%, and the other words will have some distribution. Now, the problem with maximum likelihood estimation is that it doesn't leave any mass over for dealing with unseen words. So the word wasn't seen in the document, so it's not likely, right? Well, the problem is that this document is just a sample from this underlying distribution. There's other possible documents if we took other samples. So how can we account for this fact that we have this bias, basically, by maximum likelihood? Approach is you want to smooth maximum likelihood distribution. So like Robin Hood, we're going to steal mass away from the rich, take mass away from the seen words, and give it to the unseen words. The question, of course, is who do we steal from and how much, and who do we give to and how much? This is a heavily studied problem, and there's many methods, and Chen and Goodman here is the oft-cited technical report that talks a lot about this theory. And so one of the reasons why language modeling has been so attractive to the IR community is because there is this strong statistical foundation and set of methods that they can build on, whereas you don't have this sort of thing with the TF-IDF approach historically. Now, for information retrieval, what we usually do is we interpolate the language model for the document with the language model for the entire collection. So imagine you just concatenate all the documents in the collection together and construct one language model over them. So you have now a much larger sample, so you can estimate the distribution much more robustly. Now, to some rough approximation, the collection is basically serving as held-out data for estimating the true distribution for the document. So if I have my maximum likelihood estimation for the document, and I have the maximum likelihood estimation, say, for the entire collection, somehow I probably want to adjust the document to be a little bit more like the one for the collection. Not entirely, because I don't want to lose the specificity of the document that lets me find it as being relevant, but to some extent. Now, at this point, I want to walk through a little bit of the formal machinery, because I think it also helps really nail down what's going on here, and it makes the connection back to the TF-IDF approach a little very clear. So if you just start out with Bayes' rule, we have the probability of a document given the query is proportional to the probability of the query given the document times the probability of the document. Now, everyone starts out by assuming a uniform document prior. There's been a little bit of work otherwise, but this is the general approach. And so now, basically, we're just at this problem. What's the probability of a query given the document? And this is what we've been talking about. Given a document language model, what's the probability of the query stream? Now, we're going to assume a unigram language model. This is, again, what is done heavily in the work so far. One, because unigrams are very fast to compute. And two, because the documents are so short, it's hard to collect reliable statistics over higher order dependencies. So the probability then of this entire query string is just going to be a product over each of the words, and you can view this as a sum of logs just because it's make some of the math easier later. In terms of smoothing, okay, we want to smooth our maximum likelihood estimate for the document with our language model for the entire collection. And we're going to just do it linearly here according to some parameter lambda. And you can imagine that for shorter documents, we need more smoothing than for longer documents because we have a less reliable sample, or smaller sample, so we'll have a less reliable estimate. Now, first thing I want to do is take this sum of logs here for each of the individual words and split it into the seen words, the ones I've seen at least once, and the unseen words. For the seen words, I just have this distribution, this smoothed estimate here. And for the unseen words, as we said, the maximum likelihood estimate leaves 0 mass. So the only thing left over is just this term here. And now a little bit of algebra. Instead of just generating the unseen words, I'm actually going to sum over all the words and then subtract off the mass that I mistakenly added there, so I don't double count. And then I'm going to split this last term into 2 separate pieces. And the reason for it is you can see now that this term here on the right depends not on the document at all, but just on the collection. And since our goal is to rank documents, we can basically just treat this as a constant and throw it out. Okay, so this is the equation I wanted to work towards. And what's the point of all this? Well, we see that, again, this probability of the document, given the query string, is going to be proportional to some sum here over the seen words. And for each of the seen words, what are we looking at? Well, there's this term here which is saying, how probable is this word given the document? And just, this is, again, if we've seen the word in the document very commonly, this is telling us this is a salient word for the document. So essentially what we have here is something like term frequency. Now, in the denominator, there's this thing saying, how common is this word in the collection as a whole? Because if the word is very common in the collection, then it's not very discriminating. And so essentially we have here something like inverse document frequency. And then what's going on with this term at the end? Well, we said that lambda is basically chosen that you want to smooth more, shorter documents more. So larger lambda is probably going to be for smaller documents. And this is basically acting like length normalization so that we don't penalize these short documents. So the point of all of this business was just to show that there is actually a very tight connection between what's going on in the new language modeling approach and what's been traditionally done with TF-IDF. And this is going to be also, we'll see this in the next couple of slides also. But now, of course, we have, again, this stronger statistical foundation and a set of methods for estimating these language models. So a couple simple extensions. It's a well-known adage now in estimation that there's no data like more data. If we had an infinitely long document, we could estimate these language models very accurately. But the problem is we don't. We have these shorter documents. And we can't get this infinitely long data. Either it's impossible or very expensive. I mean, we can't pay someone to manually write all the possible paraphrases of words in the document. And I don't yet have a perfect word sense discrimination system, so I can't tell you, for a given sense of the query word, which sense do I want to map up to when I'm searching for the document. So what can I do? Well, a commonly used strategy is that you can usually get similar data pretty cheaply, and it helps. Not as much as if you had the right data, but it helps to some degree. And so here what we're going to do is we're going to simulate having a longer document by mixing its language model with similar document language models. So you can imagine that we are essentially appending similar documents to the current one, and to some degree weighting how much we append them based on how similar they are. So in this case, what we're going to do is just set mixing weights proportional to similarity. So again, we can talk about using normalized, this cosine over the normalized documents, and shorter documents, the length, shorter documents, again, are going to need more smoothing. So this was actually just presented, this document expansion technique, at NACL last year. So why am I presenting this right now as sort of a core thing? Well, I think it gives a lot more intuition and understanding for what's going on with collection interpolation, which is a core technique being used in the language modeling approach. You can think of what's going on with collection interpolation as, again, we're trying to smooth this estimate we have of the short document with this collection, another language model, where the smoothing is set, the smoothing weight, some degree of similarity. And I think this is sort of a more intuitive explanation, or at least an alternative way of thinking about what's going on. And perhaps more importantly, you can see that with collection-wide interpolation, you sort of have one-size-fits-all smoothing. Whereas here, we're more specifically choosing relevant documents to do the smoothing with. So this is actually, we actually get better performance with this, and you use much less document. You use only a few documents to do this, whereas instead of interpolating with the entire collection. So it's also much more efficient. So relative to this, instead of expanding the document, you can think about expanding the query. So again, you might have this problem that the query and document talk about the same information in different ways. So you have a paraphrase mismatch. So if I had some way of guessing some other paraphrases of what the query was expressed, you could think that I might just be able to add words to the query, and then I could address this mismatch problem. The problem with just adding words is you'd somehow like to express that somehow the words the user originally gave you for the query are probably more important than these ones that you think might be relevant, but you're not sure. And the mechanism I've talked about so far doesn't really give you a way to express this. So what we're going to do is reformulate the setup slightly. So we're going to estimate a language model for the query as well as for the documents. Then we're going to compute relevance as looking at similarity between the document language model and the vector language model, and the query language model. So in some ways, we're just back to what we had to begin with. We have a vector for the document. We have a vector for the query. We're going to put them together and look at similarity between them. But again, we have better statistical theory and tools now for doing this. Question, of course, is what words do we add and how do we weight them? Simple trick, and this comes from the broad family of semi-supervised learning. We're going to run the query, and we're going to assume that the first n documents our system brings back are actually relevant. We don't know they are, but we trust our system to be somewhat reliable, at least for the top couple of documents. We then interpolate the query language model with the language models for each of these top n documents and reissue the query. And this generally improves retrieval very significantly, enough that it really is viewed kind of a core technique. Whether you're doing really the language modeling approach or in the TF-IDF family, doing this sort of query expansion really is something you need to do to have competitive performance. But it can be very sensitive to parameters. There was just this last year some work done on doing parameter-free modeling, but I'm not going to talk about that here today. Okay, so we have some idea of how the language modeling approach works in TF-IDF, and how do you evaluate, though, these systems for doing information retrieval? So metrics, at least in the States, have been driven by the TREC competitions run by the National Institute of Standards and Technology. And the documents they use, they annotate them as binary judgment, relevant or not, completely. Interestingly, they don't have enough money or time to go through and annotate every document in the collection. So what they do is they take whatever systems are competing, say 10, and for every query, they look at what are the top-end documents returned by each of these systems, and they just annotate those. So the thing to note if you're doing work in this area is that you actually have possible recall errors. If you present a very different system than what was the technology state of the art at the time these competitions were run, is you actually might find what are truly relevant documents but aren't annotated as such. So for a single query, precision tells us for the number of relevant documents our system has retrieved divided by the number of total documents retrieved. Recall, the number of relevant documents we've retrieved divided by the total number of relevant documents for this query. Now, given a document ranking, let PI be the precision at the rank of the ith relevant document. So, example what this means. If the first, second, and fifth document our system's returned are relevant, P1 is 1 over 1, P2 is 2 over 2, and P3, 3 over 5. So we've returned 5 documents, but only 3 of them are relevant. And for any relevant documents that are not retrieved at all by our system, we just let PI be 0. So average precision just says you take all of these PIs for each of the relevant documents for a query and just average them. And then for multiple queries, you essentially average this average precision over all of the different queries. So if you are looking at evaluating IR systems and you want one number, this is the number that's most commonly used, this mean average precision. So you'll see this very commonly. In terms of queries, this is also something interesting enough to look at an example or two. So TREC queries are written at these multiple levels of detail. For instance, you have a title, a description, a narrative. The evaluations that have been run for shared tasks typically have systems use title words and description words for the query, whereas research tends to just use these titles because they're more like what users do today in search engines, very short keyword queries. Now, the interesting thing is I've added some underlining to show that as you get to these longer descriptions of what the query is trying to get to, you have further restrictions or more information about what's going on. So, for example, title here of this query is antitrust cases pending. But when you look to the narrative, you see that to be relevant, the document has to identify the alleged violation as well as the government entity investigating the case. So this is something that even as a person, if you were told to find relevant documents and all you knew was this, you wouldn't know this restriction. And so you're penalized in some sense if this is all you have to go off of. Just another example that makes this one even more blatant. Title is acquisitions, and you see even in the description, the acquisition must be currently proposed and involve a US company and a foreign company. So the annotator would come in at NIST, and he would think of an idea of a query to do, and he would write this specific description of what defines a relevant and irrelevant document, and then he would go through and do the annotation. So I just think it's interesting to think about that you really have this very tough problem. I mean, if you were doing a search on acquisitions, there's no way you can know this sort of restriction here. And so I think, to some extent, this is a general problem in IR of trying to guess what the user means by a few words. But I think, to some extent, it also makes sense to think about what is being, or what information is in these various levels and which one really makes sense. If you're making an information retrieval system, which one do you really want to support most? There's even a few other fields I haven't shown. In terms of collections, this is what's standardly been used for English. These collections each tend to be about 100 or 200,000 words. Documents tend to run about 200 or 300 words in length. And the numbers I'm going to show for results are over these disks 4 and 5, which is what was done in the TREC 6, 7, and 8 evaluations. So these three TREC evaluations used this collection of documents that was about 500,000 words altogether. I'm sorry, 500,000 documents. And they ran on 50 queries. And if the truth is that for these 50 queries, there's about 5,000 relevant documents in the entire collection. So sort of a baseline number for starting, if you take this often cited inquiry system, which is just basically a TF-IDF system, you end up with a mean average precision of about 23%. If you take the basic language model we start with and just do this sort of linear interpolation with the collection language model, you have something about the same, slightly bigger, but the idea is they're roughly comparable. Now, you can do some other things. One thing I haven't talked about is there's another form of smoothing called Dirichlet smoothing, which works a little better than linear interpolation. And I think that's all I want to say right now. If you do document expansion, so instead of just estimating the language model for the document from it itself or interpolating with the collection, you interpolate the document language model with similar documents. You have a little improvement in mean average precision. If instead of doing document expansion, you do query expansion, so you run the query once, take the top 10 documents as being relevant, interpolate the query and rerun it, you have some improvement. And then these two can be put together because they're complementary techniques. And so we have about 28% mean average precision. Now, the interesting thing is I actually went back just a couple days ago and went through all of the numbers from the Trek 8 evaluation, which was in 1999. And so this is from Dow's paper from last year at NACL. And here is one of the best systems at Trek 8 in 1999. So you can see that this number is not bigger than this one, although they're somewhere in the same ballpark. So what's the take-home message from all this? I don't think we're through with all of the tweaks and heuristics yet for getting optimal performance. I think there is a path being taken with some of this recent work to try and have a more sound foundation. But I think there still is some ways to go here. And I don't know, there could well be someone here who has more background in the area that I do. I could say something after I finish the talk. Yes, so what am I doing about all of this? So the initial question I want to start out with in my own work is asking, what is the most effective language model to use if you don't worry about efficiency? So a lot of these people, they won't even consider anything besides unigram because of speed. But at least I think as an academic, we're allowed to think a few years ahead and to say something like, if I do put this aside, at least initially, can I get some kind of really demonstrable performance? So can I effectively model some of these higher order dependencies to show reductions in perplexity? I haven't talked about perplexity, but it basically is a measure of how surprised you are. And if you tightly model, if you had a very accurate language model for a given document, when you saw another sample drawn from that same distribution, you wouldn't be very surprised. So, and then related to that, the question is, how strong or how tight really is this correlation between language model accuracy, perplexity, and retrieval accuracy? And I think this hasn't been pushed on enough in the literature so far. So the basic approach I'm taking is I'm going to use a standard language model, this unigram, to just retrieve from the collection some small set of candidate documents. So let it do an initial filtering pass. And then I'm going to re-rank these candidates using a more sophisticated language model using some higher order dependencies. And there's several models to try, just of course using n-grams of higher order. So Chen and Goodman, the people I cited before on doing a lot of language modeling work, have shown that you can really get much stronger language models using word clustering, at least as you have very large collections. And I think word clustering has a very good chance to help here in the sense of if you have a paraphrase mismatch between the query and the document, it could be that the word cluster contains both of those items. So that there's some attempt to actually maybe get around the paraphrase or address the paraphrase problem directly through these sort of clustering. I also want to look at Fred Jelinek, who's often here, has a student doing random forest language models, and they're also a very interesting way to do smoothing. And then perhaps even doing some grammar-based language modeling, such as my advisor has been doing at Brown. A couple of tasks I think would be interesting to look at. So we have a problem, of course, in that not everyone speaks the same language, as you can tell here today. So relevant documents might not be in the user's native language. So the ideal system will let the user express the query in their native language. The system will return relevant documents in any language, and then the system will translate those relevant documents to the native language as needed. There's a track looking at this at CLEF this year. They have English and Czech document collections. Queries can be issued in English and Czech. And so I think this might be an interesting venue to start looking at some of these language modeling issues, because I don't think there has been any work looking at Czech at all with the paradigm. A few questions is, how robust are these language modeling techniques cross-linguistically, even if you're just doing monolingual IR in other languages? And do we serve the same sort of trends we see in English between data characteristics and performance? There's been a little bit of previous work in terms of the language modeling paradigm, I think primarily with Chinese. Perhaps even more of interest is also at CLEF, there's a track doing retrieval on speech, conversational speech. Again, they have data in English and Czech, and the conversations can be either transcripts or word lattices or audio files, depending on what level you want to deal with it. And the interest here is that we have an opportunity maybe to build on some of the previous work we've been doing at Brown in doing disfluency analysis and parsing of conversational speech in English. This is actually most of what I've been doing for the past 2 years before I started doing some of this information retrieval work. And I think that's all I want to say on that. Now, just a couple other, I think, interesting research directions, and these are not ones that I'm at least pursuing immediately. Translation models. So queries and documents are really different. If nothing else, documents are a couple hundred words and queries are a few. And yet, everything I've talked about so far talks about them like they're the same. We use the same language model for generating each. So instead, you could actually think about trying to model this well-known difference between them. And what's been done has been building what they call a translation model, inspired by work in statistical machine translation, and which is going to generate these queries from a document. And if you know about noisy channel work, you can think about that, but otherwise don't worry about it. And there has been some previous work here. Results so far, people have seen that it does improve with the basic methods, but they think that the extra time you have to spend computing isn't worth the benefit you get out of it. So that's where this is so far. Another idea I think interesting is topic or aspect language models. So documents span more than one topics, and yet we've been talking about them like atomic entities. Or we've been representing each document by exactly one language model. So instead, we could think of a document as being a mixture between some number of underlying language models. And the generative process would work something like this. You'd pick some length of the document, and then for each word position, you pick one of these topic language models, and then generate the word given that topic. There's been some previous work in this, and I'm not familiar enough with it to say where it is today, but I think it's capturing something very important here, that again, that documents are spanning multiple topics, and this isn't something that's sufficiently modeled by anything I've talked about so far. So I guess that's it for now, yes. So strengths of this language modeling approach. We have a solid statistical foundation, lots of methodology to build on, and we've seen that relatively simple models perform pretty well. Challenges is, as the one result slide I showed, I don't think these things are fully as accurate as what you can still do by tweaking other systems. So this is a real challenge. Can we beat, with the language modeling approach, these traditional systems? And then also, this real question is, what price do you pay in efficiency for doing this? So I think there's several interesting directions to explore. I need to credit Changzheng Zai, who I've been using his tutorial a lot in my own work, and it was also a basis for this talk here today. He's giving a tutorial at NACL, so if you're going, I recommend it. And for more information, you can go to my lab's webpage, or I guess just ask since I'm here. But thank you very much, and I'm happy to take questions.
Of the mean average precision of the commercial systems like Google?
No, and, well, okay, not that I'm familiar with. And then the other thing, of course, is it's a very different ballgame when you start having one hyperlink structure, of course, because we know what a strong indicator PageRank is for seeing, and then just basic usage statistics. So if there is, I don't know it, but maybe someone else also can answer if they know better than I do.
Okay, it means that you think that they might in fact be much better than these systems from the task.
They have strengths from that. Of course, the problem is the document collections, the web, is very heterogeneous, whereas these collections I've talked about so far are much more homogeneous. So I think the short answer to say is it's a different ballgame. some of the techniques I've talked about here are certainly applicable, but I think there's a lot of other things you would really need to do if you want to have accurate page retrieval on the web today.
No question from the audience. I have one rather old-fashioned remark. In the first indexing systems, I mean, looking for the keywords in documents, not every occurrence of the word was taken as having the same weight, so that there were some criteria by which the occurrences of words were weighed. And it just occurred to me that you were talking about the words or occurrences of words as if all words were equal. I mean, all forms were equal. Just a question whether you might imagine that such a kind of weighting of the words according to their position, beginning of paragraphs in the title, in the headings of the figures or things like that, might help a little bit.
Yes, certainly. So first thing I would say is I think everyone is fairly critical of this unigram or bag of words approach because it does ignore everything, even about relative context of word windows around where the doc is. And so the initial thing I'm starting to look at with these higher order dependencies is to at least look at the very local context around the word so that you will have different estimates for importance based on that. But yes, certainly words in a title are much more likely to be important than words in the rest of the document. Caption words are also very important in articles. So yes, it seems very clear that modeling that is going to matter. I think what is one thing very exciting or interesting about the language modeling approach is that it's doing so well without doing any of that so far. And I think a lot of these tweaks that people are doing is exactly this sort of thing. So maybe a challenge is going to be helping to define what is a real theory for how to set all of those weights of the different parts based on it. And quite honestly, I'm not very familiar with a lot of the classic work on this, and so there could be more theory there than I'm aware of. So.